Hi, welcome to my channel. I am Aravindan. This is the second lesson in electric field, mainly focus Cambridge, Edexcel, International Baccalaureate, AQA, OCR, A Level syllabuses. In the first lesson, we learned about electric field strength, and Coulomb's law. And we learned three different equations. Those are F equal QE. The second equation, the Coulomb's law, the force between 2-point charges K Q1 Q2 over R squared, or F equal Q1 Q2 over 4 pi epsilon naught R squared. We learned those. I told both will give the same numerical value, where K is Coulomb's constant 8.99 10 to the power 9 Coulomb, Newton per Coulomb minus Newton per meter squared, per Coulomb minus 2. The unit is Newton per meter squared per Coulomb minus 2. K can be given in terms of permittivity of free space, that is 1 over 4 pi epsilon naught. You can use one of these equations to find the electrostatic force between 2-point charges. Then we learned about electric field strength created by a point charge at a distance r from it is given by kq over r squared. Okay, good. Today I am going to do some questions mainly based on past paper questions. So these questions appeared in all syllabuses, what I mentioned: Cambridge, Edexcel, AQA, OCR, even International Baccalaureate. These type of questions came, but I start with simple questions. So this is the first question, right? The first question, in which I mentioned like X and Y are two different points and 2-point charges. 20 microcoulomb and 10 microcoulomb are kept, and XY 5 centimeter apart. Very simple question, just to learn how to use these equations. First few questions, then we'll go and we'll do mostly exam based questions. The first question, right, first part, find the electrostatic force on the 10 microcoulomb charge and state its direction. So simple, that one we can directly use the Coulomb's law. You know the Coulomb's law, that it says, first part, F equal K Q1 Q2 over R squared. K is the Coulomb constant, that is 8.99 10 to the power 9, but we can make it as 9 into 10 to the power 9. Very close a value, right? So I'll use 9 into 10 to the power 9. In all my questions, I am using 9 into 10 to the power 9 rather than 8.99 10 to the power 9. Very close the values, right? Okay. Into Q1 is 20 microcoulomb. So micro means 10 to the power minus 6. Into Q2 is 10 microcoulomb. 10 into 10 to the power minus 6 divided by R is the distance between them, 5 centimeter, convert to meter, 0.05. If you divide 0.05 and you divide this by 100, so it will be 0.05 squared, and solve it, you will get the answer. First part, you will get 720 Newton. Okay, this is the answer you get for the first part. Second part, I asked you to find the electric field strength at point Y. So what's the direction? State the direction means they will move away from each other. So the force acting on 10 microcoulomb, so they are not marked. Positive sign normally we don't mark. If it is negative, we'll mark negative sign, but positive we normally don't mark. So it's positively charged particle. They'll repel each other. So the direction of the force acting on 10 microcoulomb will be away from 20 microcoulomb. So it will move away from it. Second part, I asked you to find the direction of find the electric field strength at point Y. So that I can directly find by using the definition. Yesterday I told electric field strength at a point is defined as the electrostatic force per coulomb. So I know when I keep a charge of 10 microcoulomb at point Y, it experiences 720 Newton. So the electric field strength at point Y is given by F over Q, force per coulomb, that is 720 divided by Q, 10 microcoulomb, 10 into 10 to the power minus 6. So you will get the electric field strength, that will be 7.2 into 10 to the power 7 Newton per coulomb, or 72 into 10 to the power 6 Newton per coulomb. That's the answer for the first question. And what will be the direction of electric field strength? Okay, imagine this is a positive charge. If I keep a positive test charge here, that will be repelled by 20 microcoulomb. So the direction of the electric field strength also away from X. So the direction will be away from X. Okay, so this is the second question in electric field. So you know hydrogen. In hydrogen, electron orbits the nucleus at a distance of 5 into 5.29 10 to the power minus 11 meter, according to Bohr model. In Bohr model, we say the electrons orbit the nucleus in different shells in a circular path, is it? So here they are saying the electron is orbiting the nucleus at a distance of 5.29 10 to the power minus 11 meters. And mass of the electron is given, charge of the electron is given. So charge of the electron is negative 1.6 10 to the power minus 19 means charge of the nucleus will be positive. Normally hydrogen is a neutral atom. So neutral atom means the nucleus consists of protons. So its charge is positive 1.6 10 to the power minus 19 coulomb. So that we don't need to give it because students should know if it is a neutral atom, the nucleus should be positive and should carry the same amount of charge. Hydrogen consists of only one electron, right? So first part, find the centripetal force on the electron. You would have learned that in circular motion, when an object moves on a circular path, it needs a resultant force towards the center of the circular orbit. Why does it need a resultant force? Because when it moves on a circular path, its direction continuously changes. So since the direction continuously changes, it should have an acceleration towards the center that is called centripetal force. The resultant force towards the center of the circular orbit is called the centripetal force. So when we consider any atom, for example, this question, hydrogen atom, when we consider, so the nucleus is at the center and the electron is orbiting the nucleus on a circular path. So this is the nucleus. So if I say the electron is here, it needs a centripetal force. So centripetal force is not a type of force. That's the resultant force. So when we consider an electron in an atom, the centripetal force, the required centripetal force, we should say the required centripetal force is provided by the electrostatic force between the nucleus and the electron. So first part, they asked to find the centripetal force on the electron. Looks like something related to mechanics, but actually this is electrostatics. The centripetal force is provided by the electrostatic force. So we can find the centripetal force, that is the electrostatic force, by using Coulomb's law. So the first part answer, we can find it by using Coulomb's law. So I can say centripetal force, I'll denote it by Fe because it's an electrostatic force, is equal to K Q1 Q2 over R squared. So that is 9 into 10 to the power 9 into Q1 is charge of the nucleus 1.6 10 to the power minus 19. Charge of the electron negative, but we don't use the negative sign because we are not using, I'm not using vector signs here. It's not a vector, but when I use negative, I can explain based on vectors the direction of force, but in A level, we are not using it. So I just deal with magnitudes, that is 1.6 10 to the power minus 19 divided by R square is the distance, that is 5.29 10 to the power minus 11. All in square. If you solve it, you will get the centripetal force. That will be 8.23. Check the answer. Yeah, it's correct. 8.23 10 to the power minus 8 Newton. So that will be the centripetal force, required centripetal force, and that is provided by the electrostatic force. Right. Second part, find the speed of the electron. Okay, that is something related to circular motion, mechanics, nothing related to electrostatics or nothing related to electric field. So sometimes questions are combined, like electric field with the mechanics. So second part I can find. So I found the electrostatic force. You would have learned in circular motion. we can say V equal R omega. Okay, sorry, we can, they ask me to find the speed. Sorry, I can use F equal mv squared also. Third part I did it. F equal mv squared over F equal mv squared over. So F is the centripetal force that we know, 8.23 10 to the power minus 8. Mass is given 9.11 10 to the power minus 31 into V squared is the question. R we know the radius, that is the distance from the nucleus, that is 5.29 into 10 to the power minus 11. Okay, solve it and get the value of V, cross multiply, divide this and take the square root, you will get the speed, that will be 2.19 into 10 to the power 6 meter per second. So that's the speed of the electron around the nucleus. Okay. Right, third part. We'll do the third part. Find the frequency of circular motion of the electron. So that we can find, so for frequency of the circular motion, I can find it by using V equal R omega, that you would have learned again in circular motion. We know the V. So third part, I can find by using V equal R omega, and omega equal, that is angular speed, is equal to omega equal to 2 pi f. Okay, so I can find the third part by using V equal R omega, omega equal 2 pi f. F is the frequency, this is the angular speed. You would have learned that in circular motion. So I know the speed, V I know, that is 2.19 10 to the power 6. R is the radius of the orbit, 5.29 10 to the power minus 11 into omega, I can say 2 pi f. Solve it, you will get the frequency of the circular motion, that will be almost 6.69 10 to the power 15 hertz. That means every second it will complete this much of circular motion around the nucleus. Okay, so this is the third question. So here we are going to find the resultant electric field strength at a point when there are more than one charge. So there are two charges actually. When there are two charges, how to find the resultant electric field strength at a point in space. Okay, so the question says that X and Y are two different points and P is a point between X and Y. On the line connecting X and Y, P is a point. P is at a distance of 2 centimeter from X, where 15 nanocoulomb, nano means 10 to the power minus 9. And at a distance of 6 centimeter from Y, where 20 nanocoulomb is kept. Right? So first part, find the resultant electric field strength at point P and its direction. So we need to find the direction of the resultant electric field strength at point P. Okay. How should we do that? So imagine the point P. So imagine if I keep a positive test charge at point P, this one will repel it. And I know the equation to find the resultant, find the electric field strength at a point, at a distance from a particular point charge. We use E equal KQR square. That gives the magnitude. But how can I find the direction? If I keep a positive test charge, this will repel because this is also positive. At the same time, this also will repel. So if I draw the point P alone, this is the answer, right? In the answer, I can say point P, consider point P. If I keep a positive test charge at that point, what will happen? The 15 nanocoulomb will repel it. So the electric field strength at point P due to 15 nanocoulomb, if I say E1, that will be this direction. I found the direction. E1 is towards right because positive test charge will be repelled by this positive 15 nanocoulomb charge. Same way, this 20 nanocoulomb charge also will repel the same test charge. So if I say the electric field strength due to 20 nanocoulomb at point P is E2, the direction of E2 will be this way. Okay, by using the equation, general equation E equal KQR squared, I am going to find E1 and an E2. And we know that it's a vector quantity. So if we have two different vectors on the same line in opposite direction, we know how to find the resultant vector. That's all we are going to do, right? So I'll find the E1 first. E1 equal K9 into 10 to the power 9. Q is actually for E1, Q is 50 nanocoulomb. So 15 into 10 to the power 9 divided by R square, that is 0.02 because 2 centimeter convert to meter, divided by 100. So 0.02 square. If you solve that, the direction will be towards this way. I already mentioned that E1. So if you solve this, you will get 33.8 into 10 to the power 4 Newton per Coulomb towards right. Same way, E2 is equal to K is 9 into 10 to the power 9. The charge is 20 nanocoulomb, so 20 into 10 to the power minus 9, 10 to the power 9 divided by R squared is 6 centimeter, that is going to be 0.06 squared. So solve it. The direction will be E2 towards left. So if I solve that, I'll get 5 into 10 to the power 4. 5 into 10 to the power 4 Newton per Coulomb. So at point P, there are two different direction of electric field strengths by 50 nanocoulomb and 20 nanocoulomb. They are in opposite direction on the same line. Electric field strength is a vector. I know the magnitudes. So the resultant electric field strength I can call ER. The resultant electric field strength will be, you know, this is larger than this. So that should be 33.8 minus 33.8 into 10 to the power 4 minus 5 into 10 to the power 4. So that will be, final answer will be 28.8 10 to the power 4 Newton per Coulomb. The direction, this is larger, 33.8 is larger, that is towards right is larger. So the resultant will be towards right. So that's the answer for the first part. Okay, second part. Now what they are doing, they are keeping a charge of 20 microcoulomb. It's a positive charge. When they keep a charge of 20 microcoulomb at point P, they're asking to find the magnitude of the resultant force and the direction. So they ask you to find the electrostatic force acting on 20 microcoulomb charge when it is kept at point P. So I know the resultant electric field strength at point P. I can use F equal QE, right? So if I keep a positive charge, it will experience the electrostatic force along the direction of field line. Remember that electrostatic force on a positive charge will be along the direction of the electric field or direction of the electric field. If you keep a negative charge in an electric field, the direction of the electrostatic force acting on the negative charge will be opposite to the direction of electric field. Okay, electric field, I mean electric field strength, opposite to the direction of electric field strength. That will be the direction of force acting on a negatively charged particle. This is a positively charged particle, so the force will be along the same direction towards right. So I can find the electrostatic force acting on 20 microcoulomb, second part. Simply I can find F equal QE. Use the equation F equal QE. We know that. We know the charge, that is 20 into 10 to the power minus 6 into electric field strength. I just found it now, 28.8 10 to the power 4 solve it, you will get the answer. That will be 5.76 Newton, and direction is towards right. That was the direction of the resultant electric field at point P. Okay, so in this question, x, y, z, p is a square. In space, they are just virtual points. It's not actually a square. It's not a rigid material. Just 4 different points in space, right? So they form a square x, y, z, p, and length of one side is 10 centimeter. A charge of 6 picocoulomb positive charge is kept at x, and a negative charge 10 picocoulomb is kept at z. And the first part of this question is find the resultant electric field strength at point P. Okay, so same thing like earlier, we are going to find the resultant electric field strength due to 2 different electric field strengths created by 6 picocoulomb and minus 10 picocoulomb, right? So imagine, so I'll draw the same diagram again. Okay, answer. So if I consider this is the square, so this is 6, this is a positively charged particle, so it's a positive 6 picocoulomb, and this is negative 10 picocoulomb. So this is the point P. They're asking about this point. So imagine if I keep a positive test charge at point P, what will happen? That will be repelled by this 6 picocoulomb because they are positively charged. Both are like charges. So I can say the electric field strength at point P due to 6 picocoulomb will be this direction. I can call it E1. I'm going to find E1, but I can name it as E1. Same way, when I keep a positive test charge at point P, that will be attracted by this negative charge, because unlike charges attract each other. So the direction of the electric field strength at point P due to this negative charge will be this way. I can call it E2. So now I'm going to find E1 and E2 separately by using E equal KQ over R squared. You know the equation we learned yesterday, E equal KQ over R squared. By using this, I'm going to find E1 and E2 separately. And these two vectors are in right angle to each other, and we know the resultant vector. How to find the resultant vector? Maybe the resultant electric field strength, that is the resultant vector, will be along this direction. I can call it this way, that is ER. I can name the resultant electric field strength ER, and it makes an angle theta. So I know how to find ER by using Pythagoras theorem, because these two vectors are perpendicular to each other. So I'll find the E1 first. E1 is equal to, that is this direction, K Q over square, that is 9 into 10 to the power 9 into Q is 6 picocoulomb, 6 into 10 to the power minus 12, pico 10 to the power minus 12 over R squared. So each side is 10 centimeter, the length. So 0.1, if you divide this by 100 to convert to meter, that will be 0.1 squared. So solve it. You will get answer for that. Answer will be 5.4 Newton per Coulomb, this direction. Same I can find E2. So that is towards right. K is 9 into 10 to the power 9. Q is 10 picocoulomb. 10 into 10 to the power minus 12 over R squared. Once again 0.1 squared. So E2 will be, the direction of the value of E2 will be 9 Newton per Coulomb. These two are vectors, is it? So if I sketch a vector diagram, the 9 Newton per Coulomb will be shown like this, 9 Newton per Coulomb, and 5.4 will be shown like this, 5.4 Newton per Coulomb. You would have learned this under vectors, yeah? And the resultant will be from starting point to finishing point. This is the vector, is it? This is the resultant vector, ER. And I can say the angle with horizontal line is theta. Now I can use Pythagoras theorem. So I can say ER squared equal 9 squared plus 5.4 squared, and find the ER. Take the square root of it. You will get the ER 10.5 Newton per Coulomb. And I need to find the angle, so I can use trigonometry. Tan theta equal opposite 5.4 over adjacent 9, and take the theta inverse. You will get almost 31 degree. Okay, so that's the direction. So this will be 31 degree, and this value is 10.5 Newton per Coulomb. Okay, so now the second part of the same question, question number 4. Now they are keeping an electron. Now an electron is kept at point P, and the question is find the electrostatic force acting on the electron, and we should tell the direction also. So I already found the electric field strength at point P, and we found it, like I drew it again. The resultant electric field strength at point P is 10.5 Newton per Coulomb, and we found the direction that makes an angle 31 degree with the line PZ, right? So when you keep a electron at that point, we can find the magnitude of the electrostatic force on the electron by using F equal QE. We can find the direction of the resultant force or electrostatic force acting on the electron. But remember that in an electric field, when you keep a negatively charged particle, it will experience the electrostatic force opposite to the direction of electric field. I mean, electric field means electric field strength. So the negatively charged particle will experience electrostatic force opposite to the direction of the electric field. So we found the direction of the electric field at point P is along this way. That makes an angle 31 degree. So when you keep a negatively charged particle electron, it will experience electrostatic force on the same line opposite way, in opposite direction. So that means if I say this is the point P, so the electric field strength is this way, so the electrostatic force will be this way. The electrostatic force on the electron will be this way. That will make angle, same angle, 31 degree. Okay, so I can find the magnitude by using F equal QE. Charge is given 1.6, the magnitude 1.6, 10 to the power minus 19 into 10.5. That's the electric field strength. So that will be, you will get the final answer of it. Solve it. You'll get the final answer for that one will be 1.6 into 10.5. That will be along that direction. Okay, so the resultant force on the electron will be 1.68 10 to the power minus 18 Newton, and the direction will be opposite to the direction of the electric field strength at point B. That will be along this way. Okay, so we'll continue some more questions in my next video. Okay, right. Thanks. Bye.